All right, chemistry, this is your video lecture for chapter 6, section 5, at least the first part of it. We're going to start by talking about molecular shapes as we enter this section titled Molecular Geometry. Today, what I'm hoping you can do, predict the shape of a molecule using VSEPR theory. VSEPR theory is something we're going to introduce in this section. And then associate the polarity of molecules with the shapes of molecules and relate the polarity and shape of molecules to the properties of that substance. All right, there are only two goals here, two objectives for today's lecture, but this is a pretty loaded set of objectives. Okay, using the VSEPR theory to predict shapes is a pretty difficult thing. It takes a lot of practice. We'll be doing that in class. During this video lecture, you really want to focus on trying to get the ideas behind VSEPR theory down, and we'll practice actually predicting or drawing shapes in class. Anywho, let's get started. So, determining molecular shapes. The three-dimensional shape of a molecule is important in determining the molecule's physical and chemical properties. If you remember last year from biology, you learned about something called an enzyme. It's a protein that is shaped in a particular way in three-dimensional space. Okay, that peptide chain is bent in very specific ways. Now, if you change the shape of that enzyme, it no longer works. That's one of the reasons that running a temperature or running a fever is dangerous, because you run the risk of denaturing or changing the shape of those enzymes in your body. If you were to change the shape, it changes their function, okay? Or that is to say, they no longer function how they should, and you die. And so the three-dimensional shape of something is very important. We use VSEPR theory to predict those shapes, okay? Now, you can use a Lewis structure to help predict that molecular shape, even though the Lewis structure is two-dimensional. Okay, we're going to predict three-dimensional shapes using a two-dimensional Lewis structure. And we do that using VSEPR theory. Now, VSEPR is an acronym that stands for Valence Shell Electron Pair Repulsion. And it is a theory that predicts some molecular shapes, not all, but a good amount, the ones that we are going to worry about. Predicts some molecular shapes based on the idea that pairs of valence electrons surrounding an atom repel each other. Again, go back to that acronym, Valence Shell Electron Pair Repulsion. Again, this idea behind it, according to VSEPR theory, the shape of the molecule, which is an important thing, the shape of the molecule is determined by the valence electrons surrounding the central atom. Again, valence electrons, VSEPR, valence shell electron pair repulsion. Now, the reason they repel one another is they're negative, right? We're talking about electron pairs. The electrons are negative, therefore they repel one another. What that means for us in predicting the shape of a molecule is anytime we have a pair of electrons, okay, whether it's a lone pair or a bonding pair, we can assume that those electrons are going to become as far away from each other as possible because they repel one another. All right, so let's look at some examples. These are Lewis structures. You've seen these things before. You can draw these things. For example, CO2. When you draw this out and you finally satisfy all the number of bonds that carbon wants to have and all the number of bonds that oxygen wants to have, you see that carbon has a double bond to one oxygen and a double bond to a second oxygen. But you'll also notice that those double bonds are spread out as far away from each other as is possible. We don't have one double bond and then another double bond coming out 90 degrees from the first double bond. It's at 180 degrees. That's at the largest distance from each other as is possible, and that is going to be predicted or anticipated by VSEPR theory. If we look at BF3, there are three single bonds here. There are three individual boron-fluorine bonds. We are going to spread those out at maximum distance from one another. Okay, these two oxygen carbon bonds are spread out at 180 degrees. We have three fluorines here, so we got to spread these out. They're not going to be at 90 degrees like the Lewis structure suggests, and which is fine. This is a correct Lewis structure. There's nothing wrong with this. It's just two-dimensional. We're trying to predict three-dimensional shapes here. So we have this boron that's central, and we're going to spread these fluorons out at maximum angles. Okay, we have 360 degrees. We have 3 different bonds to make up, and so 360 divided by 3 is going to put us at 120. So these are 120 degrees apart. Let's look at methane. Okay, methane is a very common example used in general chemistry, well, and in organic chemistry as well. But we're going to see this a lot, and one of the many reasons it's a quality example is that it forms a tetrahedron. Notice this Lewis structure of methane up here. You have your central carbon, and then you have 4 hydrogen atoms singly bonded to the carbon. There are 4 bonds here. Well, these 4 bonds aren't going to be at 90 degrees to one another, okay, because they don't inhabit 2 dimensions. They inhabit 3 dimensions. They can spread out into more dimensions than just the x-axis or the y-axis. They have the z-axis as well. And so we look at this diagram over here, and we see that they have the central carbon, and each of these 4 hydrogens are spreading out into 3-dimensional space, so they're about 109.5 degrees away from each other in different orientations. The reason that they take this formation or these orientations is because this is as far away as they can get from each other as possible, meaning the bonding pairs in between each carbon and hydrogen here represented by these kind of green balloons.
The atoms attached to a central atom spread out from each other as much as possible. But how does this model explain the geometries of molecules with non-bonding electron pairs? The nitrogen atom in an ammonia molecule has 1 non-bonding pair of electrons. These electrons also repel the adjacent atoms and do so even more strongly. The atoms, therefore, are pushed closer to one another. We can predict the geometries of molecules by considering the locations of all the electron pairs in the valence shell. Phosphorus trichloride, for example, is made up of a central phosphorus atom attached to 3 chlorine atoms by single bonds. Consulting the periodic table, we see that phosphorus has 2 valence electrons in s orbitals and 3 valence electrons in p orbitals. The chlorine atoms all have 7 valence electrons, 1 empty spot in one of their p orbitals. So each of the single p orbitals in phosphorus must be bonded with the single p orbitals in chlorine, leaving a lone pair of electrons on one side of phosphorus. According to our model, the geometry of phosphorus trichloride, therefore, is not trigonal planar, but rather trigonal pyramidal, with the chlorine atoms bent away from the lone electron pair. And
so what Robot Lady is doing for us there is expanding our idea of electron pair repulsion. It's not just bonds like we looked at with CO2. The bonds are as far away from each other as possible because those are bonding electrons, but also lone pairs of electrons. If an atom has a lone pair of electrons, they are going to spread out as far away from each other as is possible. Okay. For example, we have oxygen over here has 2 lone pairs. They're not going to be right smack dab to one another if they don't have to be. They're going to spread out as far as they can. And we looked at this CH4 tetrahedral shape. Okay, can orient itself like this in 3-dimensional space. However, if it's only CH3, that's not really going to be a thing. But if we were to replace one of these hydrogens by a lone pair of electrons, that lone pair of electrons is going to repel the existing CH bonds, carbon-hydrogen bonds, in the exact same way that these electrons within the CH bond that actually is here would do normally. Okay, it's any kind of electron, electrons in a bond or electrons that form a lone pair. So let's try a sample problem here. I want you to try to predict the shape of H2O. Now I'm going to walk you through this one. I'm not going to throw you under the bus here. The first thing you want to do is draw the Lewis structure for H2O. That's the first thing you want to do. And if you need to use your 6 steps from the last note packet, feel free to do that. We want to draw the Lewis structure for H2O. Looks like this. Next thing I'm going to do, count the number of shared electrons and unpaired pairs of electrons around the central atom. Count that. How many are there? Okay. I see that Water has 2 shared pairs and 2 unshared pairs, right? 2 bonds, those are shared, and 2 lone pairs, those are unshared. So I'm going to find the shape that allows the shared and unshared pairs of electrons to be as far away from each other as possible. So I'm considering shared and unshared pairs to be essentially the same right now. So I'm going to set these electron pairs up in a tetrahedral shape. But here's the thing. These are lone pairs. Even though they are repelling the electrons in the bonding pairs, we don't count them towards the shape of the molecule. They are affecting the shape of the molecule, but we don't count them like we would an atom. Like CH4, there are 4 hydrogens that arrange themselves in a tetrahedral shape. These lone pairs of electrons are spreading themselves out because that tetrahedral shape is a very efficient shape for satisfying the repulsion of the electrons. But when it comes to actually naming the shape, we don't consider these electrons right here. We're going to consider the central oxygen, which is this red sphere right here, and then the 2 hydrogens, which would be these blue spheres right here. Now, in reality, these lone pairs that we're supposedly ignoring are pushing these 2 hydrogens down and away from each other. Okay, from both of them at the same time. So these hydrogens aren't just coming out flat at 180 degrees from this oxygen, they're actually coming down at angles. And so we have that represented right here, coming down at angles, and we call this a bent shape. Don't worry, you'll have access to a table of these shapes as we work through our practices. But this is the process you're going to go through for predicting the shape of a particular molecule. Draw the Lewis structure, consider how many shared and unshared pairs of electrons you have, and then pick a shape, pick a geometry that's going to allow those to be as far away from each other as is possible. Now, we're going to move on to polarity. Okay, so once we have the shape down, we're going to consider polarity. Now, one property that shape determines is polarity. That's why we're doing that now. The polarity of a molecule has more than 2 atoms depends on the polarity of each bond and the way the bonds are arranged in space. Remember, if we have a high degree of electronegativity difference between 2 atoms, we can end up with partial negatives and partial positives on ends of that bond. That's going to come back into play here. Now, the reason that this is the case, if 2 dipoles, okay, di referring to 2, poles referring to, a partial positive over here, partial positive over there, 2 ends of something. If 2 dipoles are arranged in opposite directions, they will cancel each other out, and we'll show that to you on the next slides. Don't worry. If 2 dipoles are arranged at an angle, okay, so they're not opposite directions, they will not cancel out. And so on the next slide, we're going to compare carbon dioxide, which is nonpolar because the dipoles are arranged in opposite directions, therefore they cancel out. And we're also going to look at water, which we just established as a bent molecule, as a bent shape. And that makes the 2 dipoles not in exactly opposite directions. They're at an angle. And so they don't cancel each other out. And so we end up with water being polar. So let's take a look at that. We have carbon dioxide up here. We have dipoles, right? Because there is some polarity, not a whole bunch, but there's some polarity between the central carbon and these oxygens. Remember, oxygen is one of the most electronegative atoms that exist, and so the electrons in the carbon-oxygen bond are going to sink a little bit closer to the oxygen, and so we're going to have some partial negativity over here. But it's going to be canceled out by the partial negativity over in this direction because it's the exact same type of partial negative. And so we have partial negative over here, partial negative over there. They're completely balanced out because they're in opposite directions. But looking at this water down here, again, we have some partial negativity up here on the oxygen, some partial positivity down here on the hydrogen. Because the oxygen is way more electronegative. The electrons in these bonds right here are going to be slid a little bit closer to the oxygen, making this area more negative, partially negative. But the thing is, these two dipoles are not in a position to cancel each other out. So this whole area up here ends up being partially negative. This area down here ends up being partially positive because these dipoles are arranged at an angle. All right, guys, I know that's a lot to take in. You might not have a clear idea of how to apply the VSEPR theory based on this video lecture, but that's why we're going to practice in class. All right, guys, I will see you next period.